35.
Okay, welcome everyone to the first lecture of the course by Andrea Guerrieri on the numerical S-matrix bootstrap. Please, Andrea.
Okay, thank you, Slava, for the introduction. So I will give three lectures on this numerical S-matrix bootstrap topic, and I will try to base most each lecture on one notebook that I will share in the channel the day before. I will try. Not sure if I can make it, but this one I already started. Okay, so to start, let me just say a few obvious words maybe about what we are going to do, okay? So it's a good idea to start different observables than, for instance, conformal correlators sometimes, because the S-matrix is an observable, a good observable in quantum field theory, and in asymptotically flat space-time, taking the due with care, you can also define it in a quantum gravity theory. So it's nice observable, that's what we are going to consider. Now, let me make a remark, maybe, just we are all on the same page, that the S-matrix is not an esoteric object, right? It's related simply to the scattering amplitude by subtracting the identity operator, okay? And the scattering amplitude is just its connected part, okay? So it's very simply related. So I will, during these 3 hours, I will change language between S-matrix and amplitude without caring much. But please interrupt me if it gets confused. But okay, this is a remark I wanted to make. Now, how do we compute it? So, well, of course, obviously, as probably most of all the observables in quantum field theory, there are not many non-perturbative methods. So one good idea is compute it in perturbation theory, right? So that's what people have done in the past, in all these years, and it works pretty well. I will use some little bit of perturbation theory from time to time. So this is one way. But in general, there are not really non-perturbative methods to compute the scattering amplitude. In the sense that even if you consider lattice, for instance, in lattice simulation, at the end of the day, from Euclidean correlators, you are going to extract the phase shift. And then to extract the actually scattering amplitude or S-matrix, you really need some analytic continuation from the phase shift. So doing lattice is like doing experiments. So that's not really a direct non-perturbative method. Of course, there is an exception that is given by integrable models, where we have example of exactly solvable theories, but these theories are not the most generic one, as integrable models have only 2 to 2 non-trivial scattering amplitudes. Okay, and all the other higher point amplitudes that usually are like n to n are obtained by factorization. So it's like products of 2 to 2 scattering amplitudes. So that's not the most generic amplitude, right? Where we can have particle production and so on. So there are no general non-perturbative methods. Let me mention one approach that I think it's very interesting, though there is only one paper that recently came out by Sasha Ziboedov and Piotr Turkin, where they revived the so-called Atkinson program. So this is just I want to make this remark, so I think it's a very interesting approach in the spirit of basically using the data that you extract from experiments or from lattice and then to analytically continue and obtain a non-perturbative scattering amplitude. Okay, so these are few initial remarks. Now, since there are no non-perturbative methods, we can rely to the Bootstrap philosophy. Okay, so instead of computing one specific scattering amplitude, specific theory, we are going to explore the space of amplitudes using numerical techniques. Okay, so the general strategy will be the following. We will have some input, okay, that will be given by the spectrum, and by the global symmetries of the system we are going to consider. Okay, and our Bootstrap will be like a black box, okay, that it will produce for us as an output bounds on observables, or physical observables. And the aim of this lecture is to describe this black box a little bit in detail. Okay, so what we do, what we can do, what we are going to do in the future. Okay, so the first question, again, two important questions one want to ask before even thinking about this black box is that what are the variables and what are the constraints? Okay, so here I'm at the introductory level. I won't go into much detail, but just to give an idea, no, what are the variables? Okay. So in general, you know, if you think about the scalar theories, so I'm not including also polarization vectors. And if we consider a system that is Poincare invariant, okay, the scattering will be a function of these invariants that are constructed by taking sum of products and squaring. Of course, by momentum conservation, they won't be at all independent, but there will be like a huge redundancy. They will be most of all will be dependent. Okay, and for this scalar amplitude in particular, there is a nice formula that says that it's like n times n minus 3 divided by 2. Okay? Where n is the total number of particles, so let me call it big N. Okay? So for instance, for n equals 4, which means 2 to 2 scattering, okay, in general, you do expect two variables, okay, two independent variables. So out of all these possible Mandelstam invariants, just two of them are independent. Okay, so these are the variables. And then, of course, there are the constraints. So this space of functions that depends on these variables that, depending on the problem, we need to specify. That is not really a generic way to classify them. You can define them in many different ways. But these functions that depends on these variables that are Poincare Lorentz invariant, okay, the space of functions is constrained. And it's constrained by the physical requirements, okay, that we also use in the conformal bootstrap, right? For instance, there will be crossing symmetry, okay, which I remind you, for instance, that if you consider a 2 to 2 scattering amplitude, it just means that if we look the function from this side, or we look the function on this side, okay, this function will be independent of how we look at it. Okay, in particular, this will be dependent on this Mandelstam invariance. So let me denote it, the amplitude as t, which is a function of st and u. Okay, that I will define later, this Lorentz invariant products of momenta. This function must be totally symmetric in the exchange of these three variables. Okay, so this is crossing symmetry, it's a constraint on this function. And then there will be unitarity. Okay, unitarity is really the physical requirement that if you consider the sum over all the possible multi-particle process, you have two particles, so you like two particles that go into n particles in the final state. Okay, so the sum of the probabilities for two particles go to n particles must be equal to 1. This will be the unitarity condition. Okay, that is unitarity condition. And then there is analyticity. And analyticity is one of the trickiest, probably. And depending on the problem, I will comment about what we assume about analyticity. Okay, but it's related to causality in a sense. But I will comment a little bit more. So,
but without analyticity, you strictly speaking cannot formulate crossing symmetry.
Without some amount of analyticity, I cannot.
Some amount of analyticity.
Yes, yes, I cannot even define crossing symmetry. Yes, crossing symmetry depends on that also. Yeah. Okay, so let me go to the plan of these lectures to be more in detail. So this is what we are going to study: space of scattering. So first of all, I will, since I'm going to talk a lot about primal, dual, primal. Okay, so I want to discuss for you some toy example that shows the difference between primal and dual. It will be a toy example that it's a prototypical example for generic S matrix bootstrap problem. Okay, so this is what I'm going to discuss, and in the today's lecture, I will focus on the primal bootstrap in 1+1 dimension for gapless particles. Okay, so we'll consider a particular physical problem, and I will illustrate the algorithm that we use to solve it. And then if there is time, I'm not sure, but if there is time, I will say a few words about also the dual version of this problem. Okay, and then in the next lecture, we will go to higher dimensions, study some gap primal problem in higher dimensions. I will provide for you notebook and integrals so you can play with if you want. And then in the last lecture, we'll be mostly focused on this dual. Okay, is there any question about the plan? Otherwise, I can. Okay. Please interrupt me anytime if something is not clear. Okay? So let's start with some toy problem. Okay, let's consider an observable, which will be for me y minus x. Okay, constrained by, and this x and y are constrained by the following constraint: x plus y squared is less or equal than 1. Okay, so here I already depicted the unit circle. X and y must be contained inside the unit circle. And what I want to ask is, what is the maximum of all? Okay, so let's first solve this problem using the primal formulation. So what would we do in the primal? In the primal, we will start to draw straight lines and see how far we can go. Okay, so for instance, I draw this straight line here that passes through the origin. Okay, which is y minus x equal to 0. And of course, my objective is 0 for this ansatz. Okay, and I can surely do better. Okay, so I can do better. Well, it's not hard to imagine that the best I can do is when this straight line is tangent to the is tangent to the disk, to the circle. Okay, to the disk. Okay, so this is the best I can do, and the maximum of this observable is therefore given by well, square root of 2. Right? Okay, so this would be an example of primal formulation. For instance, you may shoot like a straight line that goes above, okay, and then you would realize that, okay, but this is not inside the unit circle. Okay, so it's kind of direct search in the primal part. Now I want to solve this very geometric problem using the dual. Okay, so I will illustrate in detail how to formulate the dual for this simple problem. And that will be like a general lesson to apply to more complicated cases. Okay. So what we do is we define a Lagrangian. So we define a Lagrangian, which is given by our objective, plus we introduce a slack variable lambda, and we multiply our constraint like this. Okay. Now this lambda must be positive. Now, why this is a good idea? So why we are going to do this? So this is a good idea for the following reason. That, remember, we want to maximize O. Okay. Now, if I take the inf over lambda, okay, of this the inf over lambda positive of this Lagrangian, this inf is given by the following expression. It is either O, my observable, when 1 minus x squared minus y squared is positive, right? Because lambda is positive, this is positive, the minimum is O. Or minus infinity, where I'm outside the constraint. So when 1 minus x squared minus y squared is negative. Okay. So this identity is particularly interesting because now I can do the following. I can take the soup of my observable with respect to a variable x and y, and I can write it as the soup of the inf for lambda greater than 0 of the Lagrangian. Okay. This is an identity that follows from this this identity here. Now we can use the max-min inequality and exchange sup and inf. So if we change the inf and sup, we get this is less or equal than lambda positive sup over x and y. Okay, now this is unconstrained, okay, of the Lagrange. This last inequality is the core of what is called the weak duality principle. Okay, because we can do the following. We can define, so we define this unconstrained sup of the Lagrangian as a function called d of lambda, which will be the dual function. Okay. And of course, by definition, the inf of the dual function will be less or equal than d of lambda. Now let me call this inf of d of lambda as d star, and let me call this sup of my initial observable as O star. And then I got a very nice inequality, which means O star must be always less or equal than D star. Okay. Other questions? Okay. So,
should your first sub not be the sub over xy subject to the constraints of the observable? Because the observable is clearly unbounded, right? If you don't impose the constraints.
Right.
So it's a sub over xy such that the constraints are satisfied.
Right. Yes, thanks.
And then I think once you do the swap, you drop the constraints, or is it always such a?
You can drop the constraint, right? Because this inf is, you see, this inf does not depend on the constraints, either or minus infinity. But thanks for the question. Okay, so this is what we are going to do in general, okay, to swap from the primal to the dual. Okay, we are going first to we are going to perform the unconstrained, we'll take the unconstrained extremization of the Lagrangian that we can write, and then solve the problem where we minimize we take the inf of the dual function. Okay, so let me show it in practice how it works for this simple problem. Okay, so for this simple problem, we have the tower Lagrangian. Let me write it. Is 1 minus x plus lambda 1 minus x squared minus y squared. And we can do the algebra together now, right? We can find the sup of the Lagrangian. So we take derivative, get -1 minus 2 lambda x equal to 0, and then we take the other derivative, which will be 1 minus 2 lambda y equals to 0. Okay, so you see, after the first extremization, we take the sup. This is the sup, because if you take the second derivative, you will get an Hessian that is negative, defined. Okay, so after the first, so this is just x equals -1 over 2 lambda, y equals 1 over 2 lambda. So if I plug this solution inside the Lagrangian, now this does not depend anymore on the primary variable on x and y anymore. Okay, but it will be given by what? By 1 over lambda plus lambda. Then I have 1 minus, we plug this here, it's like 2 over 4 lambda squared. Okay, and this is just lambda plus 1 over 2 lambda. And the claim is that this function here, for any lambda, which is positive, it will bound the objective of my initial problem. If it was greater or equal than O star. Okay. In particular, I plot this function for you here. Okay, so this is this function that I prepared already, and you can see that the minimum is given by here, and you can check that it's square root of 2. Okay. So you see, this is an example where our original the optimal value of our original problem was given by square root of 2 and coincide with the minimum. In this case, I can just take lambda greater than or equal to 0, that d of lambda. So whenever you have a bootstrap problem, if you are able to define this dual problem, then you can put bounds from the other side. Okay. And this is the logic that we are going to use in the last lecture and maybe at the end of this lecture, so, depending on the time.
But why wherever? You did not explain what are the conditions when you can do this. I mean, you just gave some example, but it's not clear from example how general this procedure is. What are the general conditions when you can apply the weak duality principle? So the weak duality principle, I think that it's very, it's pretty general in the sense that also when you have like infinite dimensional spaces, linear functionals and then convex problems on infinite dimensional spaces, then you can prove that it holds. It's a pretty general statement, the weak duality principle. Problems arise when you consider the equality. Where did convexity, where was convexity used here?
So here I haven't used convexity. I can define the dual problem for any optimization problem, and I don't need to use convexity. What it turns out is that the dual function is convex, and that can be proven. That I left it as an exercise. Now, in infinite dimensions, what I recall is that there are nice proofs in the case when the problem is convex, and yeah, under some very generic assumptions. But I don't know much. I don't want to enter into that. But what will be used, let you see. So the reason why this is a prototypical example for a bootstrap problem is that it will be soon clear that this will be a simplified version of unitarity. Particularly unitarity is like, this is one constraint, but when we impose unitarity, we'll consider like infinite constraints, okay, in principle. And our objectives, in general, are objectives in infinite dimensional spaces. So this will be the, but all the practical ideas are contained in this simple example. That's it.
Andrea, I also have a question. If
Yes.
you go to the example page.
Yes.
So here we can see that at, sorry, the next page.
Yes.
Yeah, so here we can see that when x and y are at the solution to the first derivative equal to 0, we see the Lagrangian is at its maximum. But
yes.
Can it be some examples that the Lagrangian is at its minimum at this point, and then it doesn't seem to me clearly how this can work, because
right.
Then the Lagrangian is not bounded if it's the other way around.
Right. In that case, it would be dual unfeasible, I guess. So it's not that any problem will be feasible. I mean, will be dual feasible. That's it. But what you say, it's correct. This is a problem where these conditions are consistent and this procedure works. But if it doesn't, but in general, it might not work. It really depends on the constraint and on the problem.
So I see. Okay, thank you.
Thanks. But thanks for the question. Okay.
I have another question, Andrea.
Yes, please.
So in practice, if you have infinitely many constraints, but in practice you only impose finitely many constraints to the Lagrangian, and then do you expect that the d lambda truncated would be little bit lower, then it may not give the correct optimal result.
So let me see. Right, so you are saying that in general, it might happen that in the infinite dimensional case, the optimal dual will not coincide with the optimal prime.
Yeah.
Yeah, that's true. That's true. So in general, yes, that is true.
But is it possible that if you add some truncation, then the d lambda you get might be even smaller than theta star?
Ah, I see what you mean. No, okay. So okay, good, very good. So in all the problems that we have solved so far, we have managed to find this d of lambda analytically. So really considering the infinite constraints, all the constraints. And the truncation, it's at the level of the when we solve the dual problem. So the dual function, we do not we perform this extremization analytically. But I guess your question is relevant when you don't have, when there is no such possibility that can happen. Yeah, thanks.
Okay, thanks.
Thanks for the question.
I'm sorry, at this point I am totally confused. What can happen that d star can be, that d of lambda can be below theta star?
No, I guess the question was about whether you can perform this extremization analytically or not.
No, that was not the question. The question was that whether when you perform some sort of truncations, it may happen that d of lambda can actually become below theta star.
Right.
I hope this can never happen.
No, but imagine that you are solving this problem numerically, right? You perform the soup numerically. Then if you perform like the primal numerics, you will always be below. I mean, I don't, okay, yeah. Let's say, I don't want to enter into discussion. Let's say that for all the bootstrap problems we've solved so far, we've always managed to find this d of lambda analytically. And in that case, the d of lambda, it's always bigger or equal than the objective.
But is it by inspection, or do you have a theorem that it should be bigger?
In 2 dimensions, we found some theorem for the space of amplitudes that we consider in 2 dimensions. So assuming the S matrix or the amplitude in some Banach space and so on, we found a theorem such that weak duality and even strong duality holds. But in general, for instance, higher dimensions, I don't know.
Sorry, can I also ask again, maybe, or so it looks like if you have, let's say we have a small number of constraints, then you have a proof in the previous page that this inequality that you have here holds. Then if I add some constraints that then I don't use in the Lagrangian, it looks like this will maybe make O star go down because I'm constraining it more. But so definitely this star will still be bigger also of the new O star. So it looks like Slava is right that the wrong thing can never happen, at least in the finite dimensional case. Is this correct? It looks correct. Right, I mean, if I constrain more the objective, and I'm trying to maximize, maybe the objective will go down. But if I'm using less constraints, this is equivalent. I mean, this star will stay larger, and it was already larger than the O, which was less constrained. So I mean, it seems we're fine.
Oh, I see what you mean. So maybe I didn't understand the question.
Yeah, I agree with Marco. Yeah.
So that was the question. Okay, no, that I agree. Okay, sorry. I think I misunderstood the question. That was about the computation of the d of lambda numerically. Okay. Okay, but thanks for clarifying this point. Okay. So, okay, this we will discuss for sure later on. in other contexts also, maybe more precise, more concrete. Now let me go to what I want to discuss today, which is some example of primal in 1+1 dimensions. Okay, and I will consider like a gapless system, which is the effective field theory of a confining flux tube. Okay, so there are this very nice review that in these papers that I can that if you want to have a look, to have like an idea what is this theory. In particular, here I will tell you what we are going to use for the bootstrap. Okay. So the idea is simple in the sense that imagine that there is this infinite long strings. Okay, and we are going to write the effective field theory excitations on top of this top of the worksheet of this string. Okay. Now, we are also going to work in the limit where the string length is very small. Okay, such that you can consider the string at rest. You can fix a gauge where what is called the static gauge, where you can make the direction where the string stretches to be the x-axis. Okay, and then the time coordinate to be the time on the worksheet. Okay. Now, in this gauge, you can see that the physical fluctuations of these strings are in the transverse direction. So you would expect that you have like d-2 fields defined on top of the strings. It would be like coordinate x of I. Okay, that will depend on sigma and time. Now, these coordinates, you can imagine that you can prepare some scattering experiments, or you prepare some, you localize some this field somewhere, then you make it scatter. You prepare like a scattering state and you scatter. Okay, so we can define the S matrix. It will be a two-dimensional S matrix because it lives on the worksheet of this string. Okay, so it will be a two-dimensional S matrix. In the bending space will give us the number of fields that we have on top of our worksheet. Okay, so just to give you an idea, okay, how the action might look like for such a string is that you have an action that will start with the Nambu-Goto term, which is square root of minus g, let's call it. Let's put a normalization, which is 1 over L string square. And then we will have like a number of terms, like 1 plus, and then in principle we can have infinite terms, okay? Because if the worksheet, if the embedding space, it's not some special dimension, but it's some physical dimension like 3 and 4, okay, that we might want to look at, then this is an effective theory. It's an effective field theory. So there will be like infinite numbers of correction, this number goes. Now, let me tell you that schematically that will appear some, there will be some higher derivative operators, okay, which these operators are, they contain like 4 derivatives, okay, it's like d for x. And then we will have like another operator that I call with a k to the 4, schematically plus dot, dot, dot. Okay. Now, let me just say that this is a very special theory, okay, that we are going to consider. Because in this theory, the first non-universal correction is given by this operator here that I call with k to the 4, where k is the extrinsic curvature of this string. If you want, you can think of this k as like proportional to d dx, okay, plus dot, dot, dot. Okay. And this theory has a very constrained low energy behavior, okay? The scattering amplitude that you can construct out of this theory is a very constrained low energy behavior, because these operators here that appears, which are then would be naively the first universal, which are the rich curvature k square. One is a total derivative, the other is proportional to the equation of motions. Okay. Therefore, they are not going to contribute to the scattering amplitude. And the first correction that we expect it will be given by this k to the 4 operator. Okay. In particular, so let me write the scattering amplitude. Let me give you the result already for the scattering amplitude. The scattering amplitude will have like a term that is like s square over 2 times ls square that will be given by the 3-level interactions that come from this term, plus there will be a universal one loop contribution, plus a correction that comes from this k to the 4 operator, they call by C4, s to the 4, ls to the 6. And the fact that this one loop term is universal is due to the fact that these two operators R and k square are special, right? They do not contribute scattering amplitude, so there are no counter terms that you can add to your Lagrange. They vanish. Okay, so that's why this one loop is universal. It's totally fixed. Right. So this is the amplitude that we are going to consider. Okay. And again, when I talk about amplitude, I remind you that in 2 dimensions, the S matrix is simply related by this relation to the amplitude, I over 2s times t. Okay, so I will interchange between S matrix and amplitude. Okay. Now, let's see what are the expected analytic properties for the S matrix or the amplitude is the same. Okay. And we are going to do this in the 3-dimensional target space. Why 3-dimensional? Because again, d minus 2 when d equals 3 is just 1. So we have just one field, and the structure of crossing and everything is much simpler. Okay. Now, we do expect a cut for s greater or equal than 0 by unitarity. Okay, because unitarity tells us that 2 times the imaginary part of the amplitude is greater or equal than 1 over 2s times absolute value squared. So we do expect a cut for physical energy for s greater or equal than 0. But then what are the crossing properties? So the crossing properties for this system are such that s of minus s is equal to the S matrix evaluated in S. Okay. Now let me emphasize again that we are in 2 dimensions. So maybe if you don't, for the ones of you that you don't remember, in 2 dimensions, like think about the scattering in the forward scattering, right? So it's kind of t equal to 0, if you want to think about it. So t equal to 0, and then by momentum conservation, u it's just given by minus s. So this equation here, s of minus s equal to s of s, it's just the statement that it's the crossing, like s of u is equal to s of s. Okay. Now you may complain that this path here, okay, it's not really a path, right? Because there is a cut stretched along the whole real axis. And this is a bit of a technical point, but we are borrowing the properties that are valid for massive particles. And since this theory is a theory of Goldstone, so the low energy behavior, it's very soft, we do not expect this is going to change. Okay. So this is something that we are thinking that there is like some smooth limit as we send the mass to 0. Okay, such that the crossing properties persist also in the massless limit. And then the other property we are going to assume is real analyticity.
What would be the physical meaning of adding a mass to these Goldstones? Like I understand that, pions can be given a mass if you take quarks massive, and then this gives a mass to pions.
Right.
But and here, what is the deformation of the theory that you will be considering?
Right.
I suppose that this string came from gauge theory. So how would you deform the gauge theory to give mass to these Goldstones?
Right. That's a good question. Good. So how do we do?
I mean, perhaps since it's translations in the gauge theory that protects that makes them Goldstones, it's conservation, then you probably need to break that. So maybe curve spacetime, I would guess. And if you break translation in the original theory in somehow, then this need not be Goldstones. But otherwise, it seems hard.
Yeah, I was thinking about some gapped Goldstone, something like that. Some background such that the Goldstone are necessarily massive. So as you say, like a curved background.
Okay.
Yeah, thanks.
I think there's some example in ADS, like strings in ADS, where you also have some kind of Goldstones, but the dispersion relation is not massless.
Oh, I see. Nice. I didn't know. Thanks.
Yeah.
Okay. Well, yeah. I was more thinking about the point of the two-dimensional theory, but yeah. Okay. Now, the other point we're going to assume is real analyticity. So the fact that S star of S is equal to S of S. Okay, and this allows you to relate the value of the S matrix here to value in the upper half plane. So all in all, what we need to consider, it's just the S matrix defined in the upper half plane, and the function in the lower half plane, it's just the complex conjugate. Okay, it's just the complex conjugate of a function in the upper half plane. So this is the global structure that we are going to assume. Okay. Now, to do the numerics, okay, it's convenient to map the upper half plane to the unit disk. Okay, and this can be done by a simple, I think it's called Cayley transformation of this kind. Okay, so we use this map, chi, to map, for instance, an arbitrary point along the imaginary axis to the center of the unit disk. Then you will have that the right-hand cut will be mapped to the upper part of the unit disk, okay, and this other cut here to the lower. The threshold will be mapped to 1 and infinity to -1. So this is the map we're going to consider. In the ansatz they are going to make, okay, it's just of the form S of S will be equal to a sum over n from 0 to some n, that will be our one of our numerical cutoffs, of alpha n times k to the n of s. Okay. So we are going to consider this kind of Taylor series, truncated, of course, at some n. Okay, like for instance, an example is this simple code. And then what we are going to do? Well, this is very generic, right? This is a function that when you expand this function around s equal to 0 from above, okay, doesn't have the behavior that we want from the effective field theory, okay? So that therefore we are going to impose it, okay? So basically what this part of the code we are doing, okay? We are rewriting the condition for the amplitude to be perturbative in this way. We can package basically the soft behavior of the amplitude, saying that the S matrix behave with a phase that is like e to the I s over 4 plus I gamma 3 s cube. Here I stop at s cube, but this theory it's like elastic at very high orders. So in principle, there are many coefficients. Here there are at least 3 coefficients that can be defined, and then at order s to the 8 there is particle production. So it's elastic up to s to the 7. And here I'm stopping at order s cube. Okay, so we are basically imposing that our ansatz, okay, with just some replacement, we impose that our ansatz, when expanded for s that goes to 0 plus, has this behavior which is like 1 plus is over 4 minus s squared over 32 plus dot dot dot. Okay, and gamma 3 will appear explicitly in the expansion of our ansatz. Okay. Okay. So now we have an ansatz that, and you see, okay, let me just make another comment that you see, well, the price that we pay is that we solve for some of the alphas, some of our coefficients. So we remove some of our coefficients to impose the low energy behavior of this function. Okay.
I'm sorry, it's an ansatz for what? I didn't understand. Why is this ansatz? Why is the original function of S not an ansatz? Why what you call an expansion is an ansatz, but the function itself is not?
So, well,
I understand the point. Yeah.
No, I'm just saying that, I mean, you can expand it in general in this way, but in this way, it doesn't have the low energy behavior that you want to impose. I mean, it's like a generic expansion, right? It's like alpha 0 plus dot, dot, dot. Okay. Then here, I'm just saying that we want to solve for some of the alphas such that when you expand our ansatz has this fixed behavior. So if you want, this ansatz is just the sum over alpha prime, okay, which are linear combinations of alphas times chi to the n, such that when you expand, it has the expected behavior. Right. So in this way, we have an ansatz that is defined on the upper half plane in the unit disk, so it's automatically analytic in the upper half plane, and has also the expected low energy behavior. Okay, so this is the part of the code that performs this substitution. And then what we need to do is just to impose unitarity. Okay. So to impose unitarity, as it was said also before by, I don't remember who, but was making a comment that we want to impose unitarity for all points, but we cannot, right? So what we are going to do, we are going to choose a grid. Now, unitarity for the S matrix is simply absolute value of square less or equal to 1. So this is the condition that we are going to impose. And a very convenient grid that we choose is this Chebyshev grid. Okay. We don't have any deep reason to choose this grid. You can choose any other grid, but this is particularly convenient because it puts a lot of points close to in phi. So I remind you that we map the complex plane to unit disk. So phi that goes from 0 to pi is like s equal to 0 to s that goes to infinity. So this grid puts a lot of points close to 0 and close to infinity. Okay, that it turns out to be a good choice. Okay, where to impose unitarity. And then we evaluate our ansatz. We take our ansatz, we evaluate it as, which is function of phi, of our grid, of phi grid. And this is what we are going to pass to SDPD.
Actually, I'm sorry, I'm not following. I'm sorry. Yeah. Perhaps because I cannot read the Mathematica. I mean, you're supposed that we are supposed to read the equations in Mathematica. That's not, yeah, I cannot understand equations written in Mathematica. For example, you write here phi grid equals this. I don't read this, not in real time. I mean, I can decipher this.
Okay. Thanks. No,
but even before that, I don't understand what is ansatz, what is F. Yeah, I'm just lost.
Okay. So let me.
So maybe you should add the page. You should add the page or two, just empty page, and just define all the quantities because I'm lost.
Okay. So
can you add the page?
Yes. Let me see. What do I do? Okay. Yes. Okay. So what I'm saying is just the following. You take a function s, you expand it in these chi variables as a sum for n equal to 0 to n of alpha n ks to the n.
Okay.
Okay.
So far, so good.
Yeah. this function here, when you expand it for s that goes to 0 plus, has a generic behavior. Okay, will start as a, I don't know, alpha 0 plus alpha 1 plus alpha n. Then there will be like some other coefficient, right?
I can expand it for sure, but I don't understand why am I supposed to expand it if I, for example, want to impose unitarity?
No, that's not for unitarity. That's to impose the low energy behavior. Otherwise, you are not studying the scattering of Gostons. You are studying the scattering of generic particles. Okay. So we want to impose the low energy behavior because we are scattering Goston particles.
So what do I impose?
Or to impose, for instance, that this is equal to 1, solving for alpha 0, for instance, and then you impose that this S, this coefficient is 1/4, and so on.
Okay.
Okay, so impose up to the order that you are interested in, right? So in our case, the order that we want to impose this low energy behavior is basically, so it's the expansion of this exponential up to order s to the 4. Okay, so we'll have like 4 coefficients to tune in this case. Once you tune these 4 coefficients.
Which 4 coefficients?
For instance, alpha 0 to alpha 3.
Which n, which big n are you going to choose?
N great, I mean, big enough, I don't know, greater or equal than 4, for instance.
Okay.
Okay.
Yeah, but I understand how you're going to be able to solve for alpha 0, alpha 3 if you have n big n coefficients and you just, for example, impose that the sum of coefficients equals to 1. I don't see how you're going to choose for alpha 0 to solve for alpha 0, alpha 3. How can you solve for them? There's going to be some linear constraints on the set of alphas, but you're not going to be able to solve for alpha 0, alpha 3.
No, I mean, this is an expansion. So the expansion is done around S0, IS0. So the expansion is done around this point. And then you expound around 0. Okay.
I'm just not understand what does that equation mean. The last equation that you wrote, 4 coefficients, alpha 0, alpha 3. What exactly do you mean by that?
I mean that
they express in terms of the other alphas, right? They're not given values. Is that what you mean by solving, Andrea?
Yeah, by solving, I mean that you express alpha 0, yes, minus alpha 1, minus alpha n, for instance. This is the first coefficient I know by heart.
Okay.
Okay. Then, okay, I mean, this I'm solving the first equation. Then it's a coupled system of linear equation, and you have to solve them.
Okay, so this way we eliminate a few coefficients. Okay, we are left with the other ones. And then
you eliminate a few coefficients, and you are left to basically with gamma 3, let's say, and alpha 4 to alpha n.
Okay.
Let's say. Okay.
Yeah, so far so good.
Okay. Okay. So now we are our answers.
No, but I didn't understand the other previous page as well, because you said, yeah, this I didn't understand. I'm sorry.
Okay. So now you want to impose unitarity. So to impose unitarity, you need to choose a grid of points, right?
Yeah.
Where to evaluate your ansatz.
Okay.
And here what I'm saying is that a convenient choice is to define phi as, and I remember phi is the angle from 0 to pi that correspond then to s equal to 0 to infinity in the conformal mapping. Okay, so we choose a grid instead of s that is a unbounded interval, we choose in 0 pi that is bounded interval. Okay. Okay, convenient choice is this map here, pi over 2, 1 plus cos pi k divided by some big m. This is a convenient choice. choice, okay, just puts a lot of points around s equal to 0 and s equals to pi. Okay. It's like some natural, it's some natural basis somehow. And on this grid of points that can be arbitrary, right? I mean, this is just our choice. On this grid of points, we are going to impose that s of phi I, phi k, let me call this phi k, s of phi k, an absolute value square has to be less or equal than 1. Is what we are going to impose.
Okay.
Where s is the s that now depends on this parameter here. It's a linear function of these parameters.
Okay.
Okay. Good. Hope it's more clear now, but thanks anyway. Okay, so now we're going to pass it to the SDP problem to construct because we cannot just impose absolute value square less or equal than 1. So there is a nice trick that is this nice matrix. So let me write it. You will pass 1 minus imaginary part of S, real part of S, part of S plus 1. And the fact that this matrix is a semi-definite positive is equivalent to absolute value square less or equal than 1. Okay. Well, the determinant it's just right this condition, and then the entries are positive, right? Because this function is bounded by 1, the absolute value. Okay. Okay. So this is done in this part of the code that you will find in the lecture that I attached. Okay. What I just wanted to say here is this: that the unitarity can be cast in this way, and pass to, and this S will be evaluated on the phi k, so on the grid points, phi k. Phi k is evaluated on phi k. Okay. So for instance, in our, let's see, in our example here, number of points is 200, so we will have like 200 semi-definite constraints to pass to STPB. Okay. Right. Here, the minus sign here is because we are minimizing gamma 3. Okay, so the problem that we are going to solve is minimize gamma 3 subject to these constraints. Okay. Okay.
Sorry, Andrea.
Yes, please.
Why do you not have a grid along the radial direction? So you have 5 grids, and why is there no, let's say, radius grids as well?
Right, because we are going to, because unitarity must be imposed only for physical energies, and physical energies are mapped to the boundary of the disk.
Ah, okay, yes, thanks.
Yeah, thanks. Okay. Now, okay, here, this is the technical part of the code, but I tried basically, what I tried to do, probably, so the best way to run SDPB is through a script, I guess, not inside Mathematica. Inside Mathematica is a little bit, yeah, this syntax is a bit delicate, but I did it for you. Okay, so you can just use this function to basically specify the name of the file, the n max, and the centering of the conformal mapping, and then you will be able to run SDPB with your Mathematica. Yeah.
Can I ask a question about the previous slide? Sorry.
Yes, please.
Is this the, so for instance, I guess there's not just one way, right? One matrix that does the mapping you were saying. So for instance,
no.
One as a stagger that also works. So is there, there a way to, I mean, is this better for some reason, or it's just one choice and any choice works as well?
It's a 2x2 matrix.
Oh, okay, but for instance, if I just take, I guess one on the diagonals and that's a stagger, just say build the inner product. That's also a natural choice. I mean, I just would like to know if there is any reason why you picked this one, or if.
No, I just picked this. No, I just picked this one because it's somehow it's manifestly semi-definite positive for me. Because you see right away the determinant is the unitarity condition that, well, 1 minus imaginary part, 1 plus imaginary part are positive because it's bounded by 1.
Yeah.
This guy also has real entries. So it's a real symmetric positive definite matrix rather than a Hermitian one. If you put SS there, you get a Hermitian one, so you have complex numbers, and then you have to.
So would be like 1 1 SS dark. I mean probably they are just all related by changes of basis actually. Yeah. Okay. Anyway, thanks.
Yeah.
1 1 SS dagger becomes twice as big if you split it into real and imaginary.
Right.
Yeah.
Okay.
This is 2 by 2.
I see. Okay. Thanks.
Yeah. Okay. Okay. So this is a part that I did for you. That is basically Docker, Mathematica, all together. So let me summarize the logic. Okay. So in general, we write a generic ansatz, which is manifestly crossing symmetric, and in this case, also real analytic, and in the upper half plane, because we are in 2 dimensions. Okay? So it's crossing symmetric. We match with the low energy behavior when we need, as in this case, as we are studying the scattering of Goldstone particles. And then we impose unitarity on a grid of points. Okay. And the target that we choose to, and then we minimize our target using STPB. So this is the whole logic that this code of this code. Now, let me show you some very simple numerical results. Okay, this is taken from a run 0 that I performed already for you, that you can load it from the folder. Okay, in the run 0, so in the first run, it is convenient to tune the value of S0. So I remember you again, S0 is the center of the conformal mapping. So it's the one that is mapped to the origin of the unit disk. Okay, so this is where S0 goes. And it is better to study, for instance, so here I'm studying the minimum value of gamma 3 as I change this centering, S0. So you can see that there are choices that are very, let's say, very bad, and then eventually it becomes very good. So in this case, I mean, there is an accident, which is the fact that for S0 equals to 8, our ansatz is basically the analytic solution already, because it's a very simple system. So that's obviously going to be optimal. But in general, this is a scan that is important to do, to choose what is the best S0. Then I'm running out of time, actually, but I finished, basically. Okay, and then here you can see an example where we take, actually, here we're not taking our best S0, but we are taking, we take S0 equals to 4, because this problem is too simple. And S0 equals 8 is too good. So we take like a suboptimal S0 equals to 4, that I wrote below. I don't need it anymore. A suboptimal S0 equal to 4, and we increase n max, okay, the number of terms in our ansatz. And then, for instance, in this case, we observe like a very nice convergence. As you can see here, it's very fast convergence because it's a very simple problem. Okay. And this in red is, for instance, the analytic value for this coefficient gamma 3 that must be greater or equal. Then we know that the minimum of gamma 3 is equal to -1/76. Okay, so this we know, it's red, and you see the numeric and nicely converged to this point. Okay. So there is something fun that I wanted also to show, which is like how it looks like the phase shifts. Okay, so in this case, we're like the S metric is like non-analytically, so we know it analytically, but the curves that you see here are given by our numerics. Okay, and this is as a function of S. And you can see that this is a very nice physical effective field theory amplitude, right? You can see it by the matching that the real part and the imaginary part do with the perturbative, their perturbative count. Okay, so it's the real part in perturbation theory at one loop. This is the imaginary part at 3 level. Then you see that around this scale, the match is pretty good. Okay. And the scale is just given by the fact that I remind you that the amplitude starts with the square over 2 plus dot dot dot. So the three-level approximation is very good up to square s equals square root of 2. So roughly like up to here. Okay. So this is the result, but I think I will stop here because, well, I think, yeah, I'm already a bit over time. So I will stop here if there are any questions or, yeah.
Okay, thanks. I'm sure there are some questions.
So are you, I mean, there's this thing that the flux tube field theory is not a standard local field theory because it originates from a higher dimensional Q of T.
Right.
And yet you use the standard field theory axioms.
Right. So if the behavior is like e to the I s, for instance, so in that case, probably from the primal, it's not that obvious, but from the dual formulation that is written in terms of the special relations, okay, the special relations for such a high energy behavior, it's surely fine. The special relation. So the bounds that we get using the special relation that coincides with this bound are fine. Of course.
But probably not saturated. You said it's physical, but
no,
I don't know to what extent it's physical.
No, of course. I mean, the bound is not saturated by such theory. But I'm saying this class of theories are can be represented as a special relation. And it's the one that we use to make bounds, but they are not going to saturate. Of course, impose this high energy behavior, you know, since it's like a phase, you can always divide. You will also consider space of symmetrics times e to the is. Then you can strip e to the is, and you restrict to the space of functions that we consider here. Okay, so the bound will simply translate. Of course, if you ask me whether you can add also higher integrable charge in terms like e to the is cube and so on, then yeah, I get my, so I've been told that the bounds still hold for these more general behaviors, okay, but that surely are not compatible with Ransatz. Let's say.
Sorry, Andrea, did you say you can strip out e to the I? I mean, what about crossing? Isn't it s to the minus? You're saying
no, in the upper half plane.
In the upper half plane, and
yeah,
then you
yeah.
continue appropriately.
Yes, exactly.
Thanks.
Exactly.
But are these bounds saturated by the physical theories then? Like, should I strip off a factor e to the is? What's the claim about physicalness of these bounds?
And that depends on what is the high energy behavior. I mean, if you know that the high energy behavior it's e to the is, so if you make that assumption that you should strip out this factor, rewrite your bounds, but there is a simple relation there.
Yeah, I think so.
Yeah.
I mean, you say if it's e to the is times something that is constant, or right, if stripping out e to the is brings you within the realm of what you've just seen.
Yeah.
But it could be e to the is and then e to the I square root s. And then you would have a problem.
Yeah. Right. No, but then of course, in general, from just using 2-to-2 scattering, we do not expect to be able to probe this really flux tube dynamics, right? Because we know that the non-linearly realized symmetries implies, for instance, that higher order process depends on the same constant that appear in the 2-to-2 scattering amplitude. There are these soft theorems that relate higher point amplitude to the 2-to-2 scattering amplitude. So we do expect that including higher point amplitudes will be crucial to push away. Also because these bounds are supported by integrable theories. So this theory that I showed you here, it's the homological S matrix that connects the, for instance, the criticalizing fixed point with the criticalizing.
Okay.
It's the matrix studied by homological. All right, so it's an integrable. Well, it's obviously integral. It's a phase and it's one component.
I see. Okay, thanks.
A quick question. Okay, it's not so much about the physics of this model, but it's about this plot that we have here. No, exactly the plot we're looking at.
Ah, yeah.
Yeah. So this is the amplitude that describes the optimal, but that realizes some optimal value of the
Yes.
of this coupling. Can you give a sense, like, suppose I told you the coupling was not that particular value, but it was like 1% different, like the observed measure. Can you give a sense of, like, presumably there's some bound on how the curve could in principle differ from the optimal curve. Can you get a sense how what kind of range you get? Like, presumably it also gets less predictive at higher and higher S. So yeah, I don't know. Yeah, can you give a sense of how fast you get to a non-optimal theory if the coupling is slightly different?
So let's see if I understand. So I mean, one thing that you can do for sure is to study the space of the first two coefficients. So you have like an additional angle, right? So for instance, you can study instead the plane of gamma 3, gamma 5. But gamma 5, it's the subleading coefficient. And in this,
maybe let me ask it differently.
Okay.
Basically, I want to add the energy observable to that. Suppose I want to study the space of gamma 3 and say real part of the amplitude at S equal 5. Presumably, when gamma 3 is very close to the boundary, that space is very narrow, right? The allowed range for real part of S would be close to the optimal value.
I see.
Wondering if you have any sense, like, what does that space look like?
So you're asking, so let me see if I can rephrase it in another way. Maybe you want to, one way you can ask is like how the sum rule on gamma 3 looks like, maybe, or.
But I want to know how much predicts the UV.
So, yeah, I think this gamma 3 is, yeah, it comes from a very suppressed sum rule. Right, so it's like you can write it, for instance, gamma 3 or something that is morally gamma 3 as the from 0 to infinity of the imaginary part of the amplitude minus, here there is like z to the 5, then 1 over 16 z cubed. Something like that. Yeah. So, and yeah, and you see that this sum rule, it's highly suppressed. So if the UV would be different, the value of gamma 3 would not not change much, but it would be, yeah.
Okay, that kind of answers. So you expect that you can add adding a bump with an amplitude that, yeah, the higher S, yeah, the allowed range as you increase S will probably grow like a factor that's like S5 or some factor that cancels
Yeah.
Z5. So I see. But if you are to play this exercise at relatively intermediate energies, presumably the real part of S at the real part of the amplitude at energies 1 or 2 is probably very well predicted if you know that you're close to the optimal value of gamma 3.
Yeah.
Let me make a comment. Maybe it will. Well, I'm not sure it will help, but I think if you put the problem more or less like you're suggesting, of say fixing gamma 3 in the allowed range, and then just asking what are the allowed values of say real part of the amplitude at S equals 5, for example, and then you maximize and minimize. Usually these problems are not good. Like you just get, basically you get 1 or -1, just a local bound from unitarity, because the amplitude can basically have just a small blip there where it makes the real part very big and doesn't affect any integrated quantity. So whenever we try to maximize the amplitude at some fixed value of S, we don't get nice solutions.
Interesting.
So yeah, so I guess this goes in the direction Andrea was saying, that it's really difficult to get strict bounds. I don't think we can put a curve like saying the amplitude has to be between these two bands.
Yeah, that's what I was looking for.
Or fixed value of S. I don't think that's possible.
Yeah.
Thank you.
But there are also, you could imagine maybe convolving a bit with some bump function, right? Because the amplitude at the point is not necessarily a good object. May not be defined.
Yeah, that might be related. So, but then I think what you'll get depends on the width of your bump function. Yeah.
Yeah. And the question is which width is physically interesting.
Yeah. Oh, I guess one thing that I mean, for sure will push the bump up, for instance, is if you, I don't know, the profile of the imaginary part, if you put a bound on the profile of the imaginary part up to some energy, that will push the bound up. It will go in the direction of your bounds in the weakly coupled effective field theory. So if you push this imaginary part down, what will happen is that there will be resonance appearing above the scale where you suppress the imaginary part. So that will surely push gamma 3 up. For instance.
Okay, if there are no further questions, maybe we should call it a day. Thank Andrea and call it a day. So let's thank Andrea again.
Thank you.
Yeah, thanks a lot.
We'll try to improve tomorrow. Thanks. Okay.